again to this section of thermal engineering. And I welcome all of you again and again. So to the final version of our chapter, okay, combustion, which is subchapter 7. Okay, so we will have a discussion on this, and if we have more time, then we'll look at some questions pertaining to this particular chapter. Okay, so the basic content of this particular chapter will be focused on, we'll be looking at the combustion, definition of combustion, and then we will also be looking at the various conservation of mass energy in relation to combustion. Okay, and we will look at also calculation of various parameters such as air-fuel ratio, percentage theoretical air, and then we will determine also the enthalpy of reaction. Okay, so then we'll be looking at the first law, okay, of thermodynamics, its application to combustion. So before we go into details about the concept of combustion, there are certain definitions that we need to know. Okay, one of which is mole fraction and mass fraction. When we say mole fraction, okay, it is the ratio of the total number of moles of a substance divided by, the ratio of the number of moles of a particular species of a substance divided by the total number of moles of that particular constituent. So for example, let's say we have a system, a thermodynamic system that contains a certain number of moles of carbon dioxide. It contains oxygen, it contains nitrogen as well. Now, if I want to determine the mole fraction of, for example, nitrogen, this gives me, I have to know the number of moles of nitrogen divided by the total number of moles of nitrogen plus the total number of moles of oxygen plus the number of moles of carbon dioxide. Okay, so let me rewrite it over here. Okay. So we have nitrogen, we have oxygen, we have carbon dioxide. Okay, so the mole fraction of nitrogen, okay, nitrogen is given by this, is given by the number of moles of nitrogen divided by total number of moles of nitrogen, okay, number of moles of plus number of moles of oxygen plus number of moles of carbon dioxide. Okay, so that is how we determine the mole fraction. So over here, Y is the mole fraction, and I denotes the specific number of moles of a specific substance like carbon dioxide or nitrogen. And NM represents the total mixture. Okay, so the number of moles of the mixture. Similarly, if I want to find mass fraction, let's say, again, I have another thermodynamic system that consists of oxygen. It consists of, let's say, again, same thing, nitrogen and carbon dioxide, right? Or even hydrogen. So if I want to find a mass fraction of oxygen, this gives me the mass of oxygen present in the mixture divided by the mass of oxygen plus the mass of carbon dioxide plus the mass of what? Nitrogen. Okay, so this is the calculation of all these things. Now, total number of moles and mass of a substance is equal to the sum of each individual component. Okay, so like this one. So if you want to find the total mass of a, or moles or mass of a substance, you have to sum this plus that plus that. Okay, so now we are revising our idea of chemistry in our basic, what do you call it, SPM level or whatever, wherever you might have learned it. So when you want to find the molecular weight of a mixture, the molecular weight of a particular mixture is denoted as the mass of that mixture divided by the number of moles of that mixture. Okay, so if you have so many, let's say, mixtures, carbon dioxide and nitrogen, you want to find the total molecular weight of that mixture, is just, you can find the sum of the individual number of moles and then the mass of that substance divided by the number of moles. Okay, total is the total number of moles. So then this equation can be expressed in this form, okay, because of the fact that Ni divided by N will give us what? Y, you understand? And M is M. Okay, so again, we come to another definition, classical definition. Okay, so this is coming from ideal gas law. So the ideal gas equation, or the ideal gas equation, or sorry, ideal, the property for R, okay, so the ideal gas constant, okay, can be defined as the R bar divided by M, okay, so, and again, this, oh, sorry, yes, so this R bar, normally we refer to it as universal gas constant. Universal gas constant. Okay, so, and this universal gas constant is a value which is constant. It does not change. So, but this R changes. For example, if I want to find the ideal gas constant for oxygen, it is going to give me the universal gas constant divided by the mass of oxygen. Okay, similarly, if I want to find the ideal gas constant for carbon dioxide, it will give me the universal gas constant divided by the mass of carbon dioxide, like this. Okay, so, and that constant Is it okay now? Can you hear me now?
Yes.
Okay, alhamdulillah. Sorry, so, and the internet is fluctuating, so sometimes we cannot avoid this particular problem, right? So, and like I was defining the universal gas constant, okay, before there was interruption. Now, this universal gas constant, okay, is given by this, and this is the mass of the individual component or mixture. So ideal gas constant for, let's say, oxygen can be defined as the universal gas constant divided by the mass of oxygen, where this R is this. This is the value for R. So universal gas constant does not change, but the ideal gas constant for oxygen, for carbon dioxide, for nitrogen, all different ideal gases, they have different gas constants. You understand me? Okay, so now we are now want to define what is combustion. We say combustion is a chemical reaction during which a fuel is oxidized and a large quantity of energy is what is released. All right, so in combustion situation, it is the oxidation. So fuel is oxidized. Oxidation has to do with the presence of what? Oxygen and a large quantity of energy. So when you have oxygen, you have fuel, and then you have energy. Then combustion can be initiated. You understand me? So if any of this one is absent, then there is no way you can have combustion. For example, you can have fuel and energy, but if there is no oxygen, there is no combustion taking place. Similarly, you can have oxygen and fuel. If there is no energy, there is no way you can have combustion. All right? So now energy can be viewed as the ability to cause change. We all know this from our basic thermodynamics. Now there are various types of energy. Mechanical energy, mechanical form of energy. We have thermal energy, okay, kinetic energy, and so on and so forth. Okay, so here we are limiting ourselves to the thermal energy aspect, which is the heat. So the product of any chemical change or the combustion of a fuel, okay, the main product is the thermal energy, which is in the form of heat. Now, when we say a fuel is a particular substance whose chemical composition is largely by carbon constitutes a large portion or large percentage of that particular fuel. Okay, so whenever we see carbon, so we may interchange it to be fuel. All right, so whenever you have carbon with oxygen in the presence of a certain amount of energy, then there will be the product of combustion is going to be this carbon dioxide and heat. You understand? So here we are burning carbon in the presence of oxygen. All right? So now the second equation is the burning of carbon together with oxygen and some amount of nitrogen that is present in the air. So the total product now gives us carbon dioxide, nitrogen, and heat. Okay, the above equations, okay, we call as chemical reaction equations. All right. So now let us see what is a fuel. Basically, any fuel is a material that can be burned to release thermal energy. there are various large number of fuels that are available in nature. Okay, so most familiar fuels are hydrocarbons, fuels, which consist of hydrogen and carbon. Most fuel consist of carbon and hydrogen. Okay, and then their chemical formula is normally represented by CnHm. Hydrocarbon fuels exist in all phases. It exists in solid state, it exists in liquid state, and it exists in gaseous state. Okay, so for example, coal is in a solid state. It's a fuel, and it's hydrocarbon. Liquid, you can have petrol, gasoline, okay, diesel, all these are gaseous. And then for gases, you can have natural gas, LNG, LPG, propane, and the application normally can be found in electric generation and transportation and also industry. All right. So now let us see. Let us look at the various characteristics. The various characteristics of different fuel. Now, gasoline, its ignition temperature is 260. It means if you have gasoline and you subject it to 255 degrees Celsius, in the presence of oxygen, it will not burn unless the temperature reaches 260. You understand me? Similarly, carbon, 400 degrees Celsius, hydrogen, 580 degrees Celsius, carbon monoxide, and methane. You understand me? So all these fuels have different ignition temperatures or different characteristics. Now, note, the fuel must be brought above the ignition temperature in order to start the combustion. All right? So now what is an oxidizer? An oxidizer, we know from chemistry, basic chemistry, that an oxidizing agent is mainly oxygen. Okay? When you add oxygen to a particular element or a mixture, then that mixture is being oxidized. However, if you remove the oxygen from a substance, okay, then it is called a reduction. Okay, so but here we are more interested in the oxidation situation. So oxidizer is a type of chemical which a fuel requires to burn, and the source is oxygen. The oxidizer most often used in combustion process is air. So you see, in atmospheric air, there is large pool of oxygen that is present in the air, which we can make use of. You understand? Yes, so here, pure oxygen, normally the chemical formula for pure oxygen is O2, and it's used as an oxidizer only in some special application like cutting and welding. So sometimes if you go to the welding workshop, Benkel, you see that they cut some metal pieces into two, okay, using a certain probe where fire is coming out of the probe. Now, normally they burn the oxygen, the fuel. There is a special oxygen which is stored in the cylinder, okay, so which eventually used for the cutting of the metal pieces in the welding industry. Okay, so and then also in order to make combustion occurs, it must consist of, so one of the primary condition for combustion to take place is that there should be oxygen and fuel. So assuming we take this, okay, propane, and then we add it to a certain amount of air. So this is this is what was stoichiometric coefficient of the air. So now the air consists of oxygen and nitrogen. All right. So I'll explain this in details later on. Now the product gives us 3 moles of carbon dioxide, 4 moles of water, and 18.8 moles of nitrogen. Okay. Now the air over here is the oxidizer. Now, if we compare with this, here we have 5 moles of oxygen. It's burned with this propane and gives us carbon dioxide and water. So the oxidizer over here is what? Oxygen. All right. So now let us look at atmospheric air. Atmospheric air. Basic constituent of atmospheric air. So atmospheric air normally consists of 20.9% of oxygen, 78.1% of nitrogen, and 0.9% of argon. Okay, so such as, and then which can be treated as nitrogen. All right, so it means these argon are inert gases. Means they don't participate in any reaction. So we can add them to the nitrogen. Since nitrogen is also an inert gas, does not react with other elements. So the only, in the atmospheric air, we have these three components which are present, but only oxygen participate in the chemical reaction. So therefore, we combine these 2 components, which are inert gases. So when you sum 78.1 plus 0.9, you get 79. So we assume that atmospheric air consists of only these 2 components, okay? 20% of oxygen and 79% of nitrogen. So it means that for every 1 mole, so for each mole of oxygen that is present in the air, okay, entering the combustion chamber, it will be accompanied by 3.76 moles of nitrogen. Okay, let's say I have a certain container that contains atmospheric air. And this atmospheric air is entering a combustion chamber. For every 1 kilomole, kilomole of oxygen present, there will be 3.76 kilomoles of what? Nitrogen. So it's just like for every 1 mole, 1 kilomole of oxygen, there will be 3 to 4 times kilomoles of nitrogen present. Okay, so that is the idea that we are trying to put across over here. Okay, so whenever you take atmospheric air consists of 1 kilomole of, every 1 kilomole of oxygen will have 3.76 kilomoles of nitrogen. So the total number of moles of atmospheric air is given by 4.376 kilomole of air. All right. So now let us look at the various mass balance, conservation of mole and other things associated with the combustion chamber. Now, we normally say that for mass balance, the total mass of each element is always what? Conserved. So the total mass of each element is always conserved in a reaction, or let's say in a chemical reaction or in a combustion situation. Okay, so here we have total mass. So for example, if we have 1 kilogram of fuel, and 17 kilogram of air entering this combustion chamber. At the end, we will have 18 kilogram of what? The product. So this is what we call the mass balance. So the mass is always conserved, conservation of mass. So it means the total mass at the left-hand side should be equal to the total mass at the right-hand side. Similarly, the number of atoms of each element is also conserved during the reaction. All right? So, for example, when we say number of atoms, you see here, if you look into this equation, I have one atom of carbon reacting, okay, with, again, one atom. Yes, so the total number of atoms is equal to the total number of elements in the atomic mixture or mass. So, one atom of carbon plus one atom of oxygen. Okay, so this gives us one atom of carbon dioxide in the, sorry, and I'm very sorry. So we have one atom of carbon over here and two atoms of oxygen. Very sorry. So two atoms of oxygen. And then here we're going to have three atoms of carbon dioxide. Three atoms means one carbon and two oxygen. So this gives us three. So when it comes to the atomic number of atoms present, okay, in the reactant and then the product, they are always conserved. All right. So whenever you see oxygen, this is 1 mole of oxygen molecule. So this is a molecule. Okay, but it contains two atoms. Two atoms of what? Oxygen. You understand me? So don't get yourself confused between molecules and atoms. Okay. But we say that the total number of moles is not conserved. So for the conservation of moles, okay, it is not necessary that the number of moles has to be conserved. All right? So for example, here we have 1 mole. 1 mole of carbon react with 1 mole of oxygen, and then it gives us 1 mole of carbon dioxide. So you see, we have 2 moles of the reactant, gives us 1 mole of what? The product. Okay, so this is always the situation. So now let us continue with certain basic definitions. Here we have air fuel ratio. Air fuel ratio is defined as the mass of air that is present in a combustion reaction divided by the mass of the fuel. All right. So we can also have fuel-air ratio. Fuel-air ratio is the mass of the fuel divided by the mass of the air that is present in the combustion, where N is the mass, which is the number of moles times molar mass. All right? So, and it can be expressed in this equation. So now the mass, the molecular mass of, the molar mass of atmospheric air is always 29 kilogram per kilomole, whereas the molecular mass for hydrogen is 2 kilogram per kilomole, and for carbon, it is 12 kilogram per kilomole. Now we have another definition. So equivalent ratio. Equivalent ratio is defined phi as air fuel ratio for actual combustion divided by air fuel ratio for stoichiometric. I'll tell you the difference between these two later on. What do we mean by actual combustion and what do we mean by stoichiometric? Okay. Now, we have what we call complete. You see, in every combustion, okay, chamber, when we don't put more oxygen into the combustion system, the combustion will not be completed. Okay? So, but when we say a complete combustion, then we are referring to a situation where the fuel or the carbon in the fuel is completely burnt into carbon dioxide, and all the hydrogen in the fuel is completely burnt into water, and then all the sulfur which is present in the fuel is converted into sulfur dioxide. So whenever you have any traces of this element in the product, then such a combustion reaction is a complete combustion. You understand? So I'll go more into details when we start solving questions. Now, next, when we come to incomplete combustion. Incomplete combustion is a situation where you starve the fuel. Okay? It means you reduce the amount of oxygen which is supposed to participate in the burning or the reaction, so that what are the conditions that gives you idea that the particular combustion is incomplete? One, when you have carbon in the product, you have hydrogen in the product, and you have carbon monoxide or hydrogen peroxide in the product, then this is an indication that the combustion is incomplete. And what is the reason for complete combustion? Okay, so incomplete combustion is due to insufficient air. Okay, number two, insufficient mixing. And finally, dissociation at high temperatures. Okay, so dissociation at high temperatures means when you subject the fuel to a very, very, very high temperature, there will be dissociation. It means the chemical characteristics is going to change like this. Right? So now when we say stoichiometric, so now this is where a point which is very, very important. In fact, most questions you will come across this particular term, stoichiometric. Stoichiometric is the same as theoretical combustion. And when we say stoichiometric, it is the minimum amount of air which is needed for a complete combustion of a fuel. Minimum amount of air which is required for the complete combustion of a fuel. That is called stoichiometric. All right? So, for example, if I have 1 kilogram of a fuel, and this 1 kilogram of a fuel has to be burnt completely, or let's say I have 1 kilomole of a fuel, and if I want to completely burn this fuel, okay, if I supply it with 5 kilomole of the what do you call it, of the air, 5 kilomole of the air, then I'm going to have a complete combustion. But if I supply it with 2 kilomole of air, there will be incomplete combustion. You understand me? So it means 5 kilomole is the minimum amount of air which is required for this particular combustion to be completed. And this is what called stoichiometric or theoretical amount of air needed for combustion. So it is also referred to as 100% theoretical air. Okay? So the ideal combustion process during which a fuel is burned completely with theoretical air is called theoretical combustion. All right? So now in the previous example, we had 1 kilomole of pentane plus 5 kilomole of air. Okay? So be careful over here. I have told you that for every combustion situation, okay, we have 1 kilomole of oxygen, then we're going to have 3.76 kilomole of nitrogen, and this gives us 4.76 kilomole of what? Of the air. So the air is referring to this thing in the bracket. Okay, that is the air. And this 5, this is what called the stoichiometric amount or the stoichiometric moles, number of moles of air required for the complete combustion of this fuel. So now the reaction takes place like this, that all the carbon over here is converted into carbon dioxide, and all the hydrogen here is converted completely into water, and then the nitrogen comes out without participating in any reaction. You understand me? So whenever you see this in the product, then it is a complete combustion. However, in actual combustion practice, excess air is supplied in order to ensure a complete combustion. So normally in practical life situation, we normally put more air so that we can ensure, have 100% assurance that there will be a complete combustion. All right? So now, what are the conditions for incomplete combustion, or how to balance the equation? First thing is to set the number of moles of the fuel to be equal to 1 kilomole. 1 kilomole. Okay, the number of moles of the fuel should be set to 1 kilomole. That is for the balancing of the equation. And then assume or fix the possible substances in the product. And next, write down the known mole numbers. That is fuel, air, and in the product. Now set the unknown, I'll go through all this one by one later on. Set the unknown mole numbers with letters, that is A, B, C, X, Y, Z. You understand me? And then balance carbon dioxide, carbon monoxide, carbon, which is the number of carbons from the fuel. And then we have to balance water with OH, hydrogen, and hydrogen gas and hydrogen atom from the fuel. Okay, so we balance oxygen from other components from each mole of oxygen. So it is accompanied by 3.7 moles of 76 moles of nitrogen. All right. So now, in combustion, when we say excess air is the term used when the combustion air is supplied, greater than the stoichiometric air. All right. So, so that whenever we say 0% excess air is equal to 100% stoichiometric air. All right. And when we say 50% excess air, it is equal to 150% stoichiometric amount of air. All right. Now, in combustion, we can also reduce the amount of air. This is called starved. Let's say if I have 10% starved air, it is equal to 90% stoichiometric amount of air. All right. So here we want to discuss about the energy balance. Okay. So for a particular combustion chamber, in any combustion chamber, it behaves as a control volume. And you know, in any control volume system, mass goes in, mass comes out. All right. So that from first law of thermodynamics says that the net heat added to a system minus the net work should be equal to the change in internal energy, change in enthalpy of the system, or change in internal energy. Yes, it's correct. Change in internal energy. But this change in internal energy is given by this, the change in the enthalpy of the system. So from first law of thermodynamics, considering chemical reaction, okay, this can be reduced to mass of the product times the enthalpy of the product minus mass of the reactant times the enthalpy of the reactant. Okay? But in any combustion situation, there is no network output. Because if you have, let's say this is a combustion chamber, if air is coming in, and then we have fuel, let's say CH4, fuel is also coming in. So definitely there will be the product of the combustion. And this product of combustion, we are going to, for the product side, it is going to be mass times H, which is for the product. And then for the reactant side, it is going to be mass times H times the reactant. All right? As far as work is concerned, there is no work. Instead, there will be some Q net output. There will be heat output. You understand? Okay? So now we'll look at all these equations in details later on. Now let us come to some basic definitions. So in energy analysis, standard reference, when we say standard reference state, okay, standard reference is normally defined as a condition where you have 25 degrees Celsius and 1 atmospheric pressure. Okay, so the property of fuels. So properties of different fuels or different species at reference standard condition means at 25 degrees Celsius and 1 atm is normally referred to as, like, for example, enthalpy at standard reference state is represented by HO, specific enthalpy. Specific entropy is represented by SO, and internal energy is represented by UO. These are properties at standard reference state. So whenever I ask you, what is the property of, let's say, what is the enthalpy of methane at 25 degrees Celsius and 1 atmospheric pressure? Quickly, you refer to the property table. It is there. Then you find H at 25 degrees Celsius, 1 atmospheric pressure, the enthalpy will be given. Similarly, the entropy and internal energy will be given. Okay, so now let's see the enthalpy of reaction. Yes, very important. It's the difference between the enthalpy of the product at a specific state and then the enthalpy of the reactant at the same state in a complete combustion. So by definition, enthalpy of reaction, yes, so HR, this is the difference. Okay, so here we have HC is the enthalpy of combustion, and again, this is the amount of heat release during a steady flow of combustion process when 1 kilomole of fuel is completely burned at specific pressure and temperature. All right, so this can also be referred to as HR, which is enthalpy of reaction. Okay, enthalpy of reaction. Enthalpy of reaction, which is the same as enthalpy of combustion. So it is a difference between the two enthalpies. So now we have enthalpy of formation. The enthalpy of formation is the enthalpy of a substance at a specific state due to its chemical composition. All right? So, for example, carbon dioxide is formed from carbon plus oxygen, which gives us carbon dioxide, right? So we can define the enthalpy, the amount of energy which is released in the formation of carbon dioxide, and we refer to this as HF, that is enthalpy of formation of carbon dioxide. This also you can get from property table. All right? So in a nutshell, the Q, which is the amount of energy released, is the same as the enthalpy of combustion, which is equals to the difference in the enthalpy of the reactant and the product. So normally nitrogen and oxygen are considered as stable elements because of what? The enthalpy of formation is considered to be 0. And it is true. You see, here we combine carbon and oxygen to form carbon dioxide. So carbon dioxide is formed from carbon and oxygen. So its enthalpy of formation is never equal to 0. So enthalpy of formation of carbon dioxide is never equal to 0. But the enthalpy of formation of oxygen is always equals to 0, because there is no, you don't have to combine any particular element to get a product of oxygen. Oxygen already exists in its natural state. You understand me? So we don't have any enthalpy for formation for this element. Same thing applies to all naturally existing elements, such as nitrogen, oxygen, carbon. All these things, they exist in their natural state. You understand me? But we can form water from hydrogen and oxygen. We can form carbon dioxide from carbon and oxygen. So all these things, they don't exist, and we can produce them, and then through the combination of these naturally existing elements. All right? So now let us see the energy, the enthalpy of the reaction and enthalpy of the product. All right? So we are talking about this enthalpies. So we say enthalpy of combustion equals to enthalpy of product minus enthalpy of the reactant. Now, this enthalpy of reactant can be defined as the sum of the number of moles of each species in the reactant times, into bracket, the enthalpy of formation, okay, at standard state, plus the enthalpy at reference state minus the enthalpy at standard state. You understand? So let me define them one by one. So N, from this equation, okay, N equals to number of moles of elements in what? Number of elements, number of moles of each element in there, number of moles of each element. So I have over here number of moles of each element or species. Okay, number of each element in the reactant. And then we have HF. HF, okay, HF is equal to, HF bar equals to enthalpy of formation at, because of this 0, you see, this is at standard reference state. Okay, so we have let's see over here, HF bar 0. Okay, so this is the enthalpy of formation at standard reference state, at standard reference state. And then we have HT equals to enthalpy. So when I say enthalpy at standard reference state, I'm referring to 25 degrees Celsius, and what? 1 atmospheric pressure. And this is enthalpy, okay, at a given state, okay, enthalpy at a given, enthalpy at a given or reference state. All right. And then the last one, HO equals to enthalpy at standard reference state. Enthalpy, specific enthalpy at standard reference state. Okay, so don't confuse this and this. This one is enthalpy of formation at standard reference state, and this is just enthalpy at standard reference state. All right, so don't get yourself confused with this. So now we have a combustion situation where carbon reacts with oxygen and forms carbon dioxide. All right. So, of course, now you see the the reactant is going into the combustion chamber at what? Standard reference state. And then the product also is at standard reference state. So the enthalpy or the energy of combustion equals to HP minus HR, which is the same as the enthalpy of combustion. You understand me? So the difference between these two gives us minus 393,522 kilojoules per kilomole. That's the amount of energy which is released. You understand me? So we will normally refer to this in the property table. We'll look at example later on. Okay, so and these are typical example. For example, the molecular mass of pentane is this, carbon dioxide, its molecular mass is this, and enthalpy of formation of this fuel is this. Enthalpy of formation of carbon dioxide is this. Enthalpy of formation of water is this. So you see, for oxygen and nitrogen, they don't have enthalpy of formation because they exist in their natural state. You understand me? Similarly, hydrogen exists in its natural state, so that does not have any enthalpy. And this is the change in enthalpy, okay, of each particular species. Okay, so this one also does not exist because it's only a fuel. All right, and then this is also not applicable. This is also not applicable. Okay, so we will look at typical example later on. Yes, so now I have a question over here, series of questions. Okay, so let us try to discuss them before we leave. So I'll start first with this question. Okay, so let me see, let me copy it. Yes. In this question, we are told that consider the stoichiometric combustion of methane Consider the stoichiometric combustion of methane in atmospheric air. Write down a balance equation of the combustion process and determine AF. So AF means the F-well ratio. Okay? So in a question like this, first thing what we need to do is to write down. So we assume, it says that consider the stoichiometric combustion. So the word stoichiometric means complete combustion. Stoichiometric implies complete combustion. Okay. So if it is a complete combustion, then it means the chemical reaction who is going to give us, we'll have CH4 plus air, atmospheric air. And I've told you every 1 mole of oxygen that is present in the atmospheric air, there will be 3.76 kilomole of what? Nitrogen. So this is the amount of air that we assume that it is reacting with this fuel. All right. So now, since this is a complete combustion, then the product is that all the carbon will be converted into carbon dioxide. And all the hydrogen here will be burnt into water. And nitrogen only comes in and it goes out. You understand me? So we're going to have plus and most, so surprise, nitrogen. So now the next step is to balance the equation. Balance equation. How do we balance equation? First thing, we need to write down, let's see over here. You see, we don't know the stoichiometric amount of of air, which is participating in this reaction. So we represent it by ATH. And we don't know the amount of carbon dioxide which is forming the product. So we say let it be X. Also, we don't know the amount of water, mole fraction of water, which is Y, we represent it. And then let's say number of moles of nitrogen which is present, also we don't know. So this is Z. Okay. So now what is this ATH? This is what we call theoretical amount of air. Okay, theoretical amount of air, which is the same as the stoichiometric amount of air. Okay, so now one thing I need to inform you, for every combustion equation, we always assume that 1 kilomole of the fuel is reacting with a certain kilomole of air, which we don't know, this we have to find, and the product, we have S kilomoles of carbon dioxide, Y kilomole of water, and Z kilomole of nitrogen. So we need to find these parameters. First, let us balance okay, species or the mixtures species. Okay, now first we will consider carbon. So how do we balance carbon? We have 1 mole of carbon over here in the reactant. So we have 1, and this is equal to 1 mole of, or kilomole of carbon in the product, you see, which is X kilomole. So it means that X equals to 1. And similarly, we will balance the hydrogen. Hydrogen, we have 4 atoms of hydrogen. 4 equals to Y times 2. This gives me 2Y. 2Y. So it implies that Y equals to 2. And next, we will have a balance for oxygen. All right? So oxygen also, we have ATH times 2. Okay, so this gives me 2 times the theoretical amount. Okay, this should be equal to, I have X times 2. So X, or 2 times X, or 2X, okay, plus, again, Y in the water. So now, but X equals to what? So X equals to 1. So then you will have, this gives me 2 plus what? Y, 2. Again, this gives me 4, all right? So this equals to 4. So we have 4. So now, and we have 2 times ATH. So 2 cancel 2 over here, we have 2. So eventually, ATH, the theoretical amount of air, equals to 2. I hope you are getting what I'm saying. So next is to, now we know the value for ATH, we know the value for X, we know the value for Y. Now we need to balance the nitrogen. So how do we balance nitrogen? So here we have ATH times this 3.76 times 2. This gives me 2Z. You understand? So 2 cancel 2 over here. I know my ATH to be 2. Okay, so eventually Z gives me, Z equals to, if you multiply 2 times this gives me, let's see, let me use my calculator over here. Yes, so we have 2 times 3.76, 2 times 3.76. So 7.52. So this gives us 7.52. All right, kilomole. So now we're going to write down the complete stoichiometric equation. All right, so now we know all the information. So we have CH4 plus 2 oxygen. Then if this is 3.76 of nitrogen. Okay. And then this gives me carbon dioxide was 1. So I have CO2 plus water. So, and hydrogen, Y is 2. So I have 2 moles of water plus nitrogen, that is 7.52. So 7.52 of nitrogen. All right. So this is the balance equation. for the combustion reaction. All right. So now we have to determine the air fuel ratio. Now again, this is the stoichiometric equation. All right. So air fuel ratio by definition equals to mass of air divided by mass of fuel. Mass of fuel. All right. So now, how do we define the mass of the air? So this gives me, for the air, I've told you molecular mass of air equals to 29 molecular mass of air. Molecular mass of air equals to 29 kilojoules, kilogram. Let me see. Yes, so that gives us 29 kilomole. All right. And 29 kilogram per kilomole. I'm very sorry. 29 kilogram per kilomole. 29 kilogram per kilomole. Kilogram per kilomole. All right. So now, but we know that in the air we have 2 moles. That is the stoichiometric amount of air. Okay? And let me use a different color so then you understand what I want to put across. So here we have 1 kilomole of oxygen plus 3.76. So this gives us 4.376. Sorry, 4.76. I'm very sorry. 4.76. So if you add this 1 plus 3.76, so this gives us 4.76. So this 4.76 is the total moles of the oxygen. So by this stoichiometric, okay, amount is given by this. So we will multiply 2, okay, times 4.76 times the number of moles. Okay, so this gives us the kilomole. Okay, so then times the number of moles, which is the 29 kilogram per kilomole, all divided by mass of the fuel. So what is the mass of the fuel? The fuel, we have only 1 kilomole of the fuel. So I'll have 1 kilomole of the fuel times, again, so in the fuel, we have carbon and hydrogen. Okay, so here we want to determine the mass of the fuel. Oh, sorry, molar mass of the fuel. Molar mass of the fuel. Okay, this is given by 12 kilogram, okay, per kilomole of what? Of carbon plus, again, hydrogen is 4 kilogram per kilomole of what? Hydrogen. All right. So if you substitute them over here, this gives me 12 plus 4 kilomole, sorry, kilogram per kilomole, kilogram per kilomole. All right. So if you solve this equation carefully, okay, so you get AF, F1 ratio equals to 17.3 kilogram of air, okay, per kilogram of the fuel. All right. So this is the solution to the first part of this question. Okay. So I would like to stop over here. If there is any, the next question I will discuss in the next class. Okay. So if there is any question, let me hear your voice, please. Is there any question so far? Yes. Is there any question so far? Okay. So no response from anybody. Okay. So there is no question.